So without further ado, let me introduce our speaker today, Dr. Massimo Stafoggia. He's a senior researcher at the Department of Epidemiology at the Lazio Regional Health Services in Rome, Italy. He's also adjunct senior lecturer at the Institute of Environmental Medicine at the Karolinska Institute in Sweden. And currently he's a visiting researcher at the UCLA's Fielding. And it's my great pleasure to have Dr. Stafoggia being here today. Is that he has really truly one of the pioneers in conducting a lot of the temperature interaction studies. If you look at some of his papers dated in early 2000, I have actually through the years through direct collaboration, but also many other things, learning from him and his work. So it's really great honor to have him here. Among many titles, projects he has done, one thing I want to mention is that he's has leading many both international, but also Europe, multi-country level and Italy national level projects, covering from many air pollution epidemiological projects. And the last thing I want to mention is that, as you know, we a lot of work, our work is focused on studying environmental epidemiology. And Massimo's recent paper has been selected as the this year's best environmental epidemiology paper by the International Society for Environmental Epidemiology. So I think it's the excitement for us to have him today. And without further ado,
thank you very much. Good morning, everybody. It's a big pleasure for me to be here. Thank you to the organizers for this opportunity. So in this presentation, I will, as Kay said, I am an environmental epidemiologist. I am a statistician by training. So during my 2 decades of study, I tried to develop statistical methods. So I will try to focus a little bit on the methodological side, on the this topic. But of course, there will be a lot of results that we can discuss. So I'm very happy to get your comments on the methods, results, interpretations, whatever you can think of. So the topic of the presentation will be interactive effects of heat and air pollution on mortality, innovative methodological approaches. This is a topic which is very much hot, let's say. So we know that air pollution affects health. We know that extreme temperatures affect health. We don't know exactly how they interact on health, whether they, there is a synergy between the two, the independent effects are, the interaction between the two is greater than the sum of the individual effects, whether that is the same in different parts of the world. There is a lot of complexity there, and there is a lot of heterogeneous results across the world. So in this study, I will present you 2 main projects where we have been working on this topic. The first project, it is, I don't know, let's see. It's not working. Anyway, the first project is a European project. Yes, the Exhaustion project, and it's funded by the Horizon 2020. It's a very big project involving many countries in Europe. You see, the topic is about heat. Air pollution is a side in this project. The focus of the project is exposure to heat and air pollution in Europe, cardiopulmonary impacts, and benefits of mitigation and adaptation. So it's not only research, there is a lot of, public-oriented, investigation here in terms of adaptation and mitigation strategies. But it's a big project with different types of data that have been collected. You can see 3 different levels of analysis. So there is data from individual cities, the continent, with time series approaches to investigate the effect of heat on cardiopulmonary outcomes at the city level. Then there is a analysis, which is the one I will focus today, which is a small area analysis. So for a few of the countries, we were able to collect data, not just for the main, for the entire country. So cities, rural areas, small towns, villages, etc. And so the purpose there was to exploit the potential of the spatiotemporal contrasts in exposures and outcomes, especially to see whether there was some differences between rural, suburban, and rural areas when it comes to the effect of heat and cardiopulmonary outcome. And the level 3, which is here, is cohort data. So we have a few cohorts in Europe, and the idea was to investigate both long-term effects and short-term effects. And also we studied the different aspects of the relationship between temperature and outcomes. I will focus on what is green, the blue circle here, which is the interaction between the temperature and air pollution. So that was the focus of this presentation for exhaustion. Some details about the methodological steps that we have undertaken in this project, so that we can go more into the details of the study. Again, the objective was to estimate the effect of high temperatures by levels of air pollution. So in this project, we are considering air temperature as our main exposure. So we are interested in the effect of air temperature and specifically the heat. So we are focusing on the part of the relationship on the right side of the exposure response function. So if you look at the scale of temperature, we are not investigating in this part the effect of cold temperatures, but the effect of heat. And that's the first choice that we made in this project to kind of restrict the size of the study hypothesis. Air pollutants are considered in this study as effect modifiers. So the task here is to investigate whether the effect of temperature changes for different levels of air pollution. In the next project that I will talk in the second part of the presentation, we will do also the other way around. So we will see whether the effect of air pollution changes for different levels of temperature, because that is also interesting and that's part of the synergy between the two exposures. But in this part, we will focus on temperature. So as I said, we focused the study on those countries which provided the small area data. And these were 5 countries that I will present in the next slides. So we have area levels, larger area units like counties or regions, and smaller like provinces or municipalities. Or in the UK, there is this distinction between MSOA, LSOA, which are different size of units. And we will explain that later, why we decided to have different area levels. Exposure is daily mean temperature. As effect modifiers, we are considering these 3 pollutants. So just to have an understanding, all of you are more or less familiar with the air pollution epidemiology, or do you need some kind of introduction to what PM is, what ozone is? Can I assume that more or less? So PM stands for particulate matter, 10 or 22.5 is the size fraction. The finest, the fraction, the more plausible are the particles to penetrate deep into the airway system and then to translocate into the blood circulation and to affect other organs as well. So in the studies, we are considering PM10, PM2.5, and ozone as effect modifiers. So let's focus a little bit on the analytical strategy. So first of all, we couldn't pool the country-specific data all in one big data set. Each country referent analyzed their own data. So it's country-specific analysis. This meant that we had to produce a code that was standardized and that was shared among all the study participants. Each one of them ran the analysis, they sent back the results, we double-checked, and we kind of fine-tuned the process along the way. So in each country, as I said, we defined large areas, meaning, for example, just to make it simple, in Italy, we have more or less 8,000 municipalities. But some of them are very, very small. So analyzing each one of them individually was not feasible, both computationally speaking, but also in terms of statistical power. Many small municipalities contribute with very, very few cases. So it was impossible to analyze each one of them individually. So what we did was to pool the municipality-specific data into province-specific data sets. And we analyzed each province per se. So we have 20 provinces. So you can understand in each province there are I don't know, 200 to 300 municipalities. That is how we clustered our data set to make it treatable. So analyze, so the study unit is still the municipality and the day, but the data set that we analyzed one by one was the province. And we did the same in the other countries, different types of denominations. So UK, the large areas are the MSOA and the small areas are the LSOA. In other places we had counties and municipalities. Okay, so the idea is that we analyzed, for example, for Italy, each one of the 20 counties separately, then we meta-analyzed the 20 county-specific results in order to get a country-specific result. And then we put together the 5 countries to get pooled associations. Is that clear, the process? Okay. As I said, we focused on the warm season only because the project was much about heat, climate change, global warming. So even though there is an interest even in investigating the other side of the relationship, we had to kind of restrict our study in some way. So we focused the attention on the warm season that we defined as May, September. And in sensitivity analysis, we also further restrict to June to August. We will see the next project, which is based on global data. We couldn't just define based on month, because May, September is summer in some places, it's winter in others. We had to do something different, and we will see that later. In terms of models, it is a time series approach. We have daily counts of co-specific mortality, daily mean temperature, daily air pollution. So it's a Poisson regression. We applied time quasi-Poisson regression modeling, adjusted for time trends and other potential confounders. I don't think I will go too much into the details of the modeling part, but if there are specific questions on that, of course you can ask. But the idea of the Poisson regression, for those of you who are not familiar with that, is that the Poisson is based on counts. So it nicely fits into the analysis of count data, first. Second, the idea of a time series analysis is that you want to kind of, let's say, focus on the day-to-day variability between exposure and outcome. So you want to filter out long-term and seasonal trends, so that what is left to make our inference of is the short-term day-to-day variability. So this is what we did in this analysis, to analyze the data, adjusting for time trends, both to capture the long-term and to capture the seasonality aspects. Okay, so the complex part was this tensor smoother here. So the idea was that we wanted to capture the complex relationship between co-exposure to air temperature and air pollution. So that's the idea. To do that, basically what we did was trying to be as flexible as possible by considering products of splines. So we were flexible in terms of the exposure response functions, both for the air pollution and for air temperature. And we used this tensor smoother, which is basically a product of splines. You know what a spline is? It's a nonlinear function. So we relaxed the assumption of linearity, and we assumed that the relationship between temperature and mortality could be nonlinear, because this is what it is. It is nonlinear. So there is a point of temperature where the risk is minimum, and then departing from that point, you see the risk increasing, both on the left side for cold temperature and on the right side for the warm temperature. So it's a nonlinear relationship. For air pollution, it's not that clear. I mean, there is a lot of evidence that the linearity assumption might hold. So ideally, we might have kept air pollution as linear. We will see in the second project that this is exactly what we decided to keep air pollution as linear in order to simplify the interpretation and the presentation of the results. Here, the air pollution was just an effect modifier. Here, we were interested in extrapolating the effect of temperature by levels of air pollution. So we used this tensor smoother, and also we simplified the latency of the relationship, considering a lag 0,1. Lag 0,1 means that we are investigating the relationship between today's mortality and today's and yesterday exposure. We didn't go back more days because from the literature, we know that when it comes to the effect of heat, usually it is the very first days which have the strongest impact. You don't usually go much back in time. When it comes to cold effects, it is a more delayed association. Usually you would see effect even when you study the exposure 1 or 2 weeks before the outcome. But for the heat, it's more the heat wave, the very peak in exposure today or yesterday. So Lazio 1 is basically the average exposure between today and yesterday. Okay? Okay, we have to, since the effect of temperature is not linear, we have to define how to express this relative risk, this effect. There are different possible ways. In the literature, if any one of you is studying this kind of literature, you will see different ways to express the effect of heat. So you have, when I say effect, you have to define a reference point, and you have to compare the risk at some point versus the reference. That's the relative risk we have in mind. We've decided that since we were analyzing different countries and different spatial units within each country, we decided to choose some percentiles, which will correspond to different levels of temperature in each place. That's the point. We do not expect that the effect will be the same at the same level of temperature because of adaptation to different climates. Even within a country, you would have diverse, temperature ranges north to south. So we decided to be kind of relative using percentiles. So basically, we are expressing the effect of temperature for increments of temperature from the 75th to the 99th percentile of the location-specific distribution. Okay, and for air pollution, same, we have to define what is low, what is medium, what is high. And we decided to use 5th, 50th, and 95th percentile as levels of air pollution. And in sensitivity analysis, we did something different. Okay, so this is just to give you a visual representation of what we are doing. You can see this is kind of a complex relationship. You have your outcome here, where it's written linear predictor, you can imagine that as the risk of mortality. You have air pollution here, you have temperature here. And for increased temperature, you have the risk which goes up in different ways depending on where you are in this joint relationship. So the idea was to take cross-sections of this relationship at different levels of PM. So let's say low, medium, and high, and take out of these three curves, take the effect of temperature expressed from the 75th to the 99%. And the nice feature of this graph is that you can reverse and you can express the effect of air pollution by levels of temperature from exactly the same model. That was what we did in the second project that I will talk about. And the complex part was to derive standard errors and confidence intervals with that pretty defined this problem. So using a statistical artifact. Okay, so these are the countries that were involved. You can see the spatial units. And this is the maps of, mean air temperature levels. It's kind of difficult to see the ranges. It's in the centigrade, degrees centigrade. So I don't know in Fahrenheit how that converts. But there is different, of course, variability. We have Norway, which is far north, much colder. We have England and Germany, which are kind of more in the center, and then Antarctica, which represents the Mediterranean climate. And these are maps of PM 2.5 by area level. Even here you can see some variability. In Italy, we usually see this very high hotspot level in the Po Valley, which is north of Italy, which is one of the most polluted areas in Europe. And different levels in different. This is, of course, London, for example, etc. And that's awesome that we didn't have data for UK, so only a few countries. This is quite small, but just give you an idea of the amount of data we have. So this is a number of events in terms of hundreds of thousands. So the good part of the study was the power. We had a lot of statistical power to investigate even small effects. But I will go to the next. Okay, so this is a summary of the main effects that as a meta-analysis of the 5 countries. So this is the effect of air temperature by air pollution, by PM 2.5 levels, which is low, medium, and high. And these are expressed, as I said, as % change in mortality. In this case, you can see cause-specific mortality. So natural cause, cardiopulmonary, which is the sum of cardiovascular and respiratory. And then you see the 2 groups separated. And basically what we saw, which is something that we usually see, especially from European studies, it's an increasing effect of temperature for higher air pollution levels. So this is quite common to see. We ran also several sensitivity analyses where, as I said, we defined the warm period as the 3 warmest months rather than the 5. We tried to use a more extended lag definition up to 4 days, and we use different percentiles of the air pollutant as the quartiles. But basically, the main picture remains. And this is the same for Lazio. So in this case, it is less clear. I mean, in this case, we see much higher effect in the high levels, not so great difference between low and medium. So it's not a smooth increasing gradient of effect, but it seems that the interaction happens, especially at very extremes. And interestingly, this is also what happens in the global analysis from the second project I will talk about. Okay, this is just some results for the country-specific analysis. Also see that there was some consistencies across countries. In some cases, like I guess Italy, Germany, it was more pronounced. In other cases, it was a little bit so. For example, in England and Wales, it was not that strong, the effect multiplication. But mostly they were kind of suggesting the same pattern. And that is with ozone. Again, for ozone, we have some more heterogeneous associations. In some cases, also the opposite way for Norway. And we don't really know why. So if one of the questions is why Norway is the other way around, I don't know. The answer is I don't know. In short, we found adverse effect of high temperature on mortality, but that was already known from the literature, and we confirmed that in the study. We found stronger effects of high temperatures on days with high PM 2.5 concentrations, and the same also for ozone, with some heterogeneities across countries. Okay, any question? Yes, before moving to the next.
Yeah, that's really interesting. And, I mean, coming from growing up in Norway myself, I know how cold it is, and I know how warm it is in Italy. And you said that you use these percentiles, right, to reflect that we are accustomed to living in a certain climate, right?
Right.
But there might also be sort of these biological threshold points, right, where no one is dealing well with the temperature above 35 degrees Celsius, for instance. And did you look at absolute temperatures as well for this project, or just
this
relative?
project we didn't? I mean, in other projects, what we did was more investigate the heat wave part, exactly to go in the direction you are saying. I mean, if it is above some threshold, still location specific. It's still, we haven't used the absolute values because it will be very difficult even to find a common support in some countries. But if it is above some very high percentile, prolonged for several days, maybe that is when something triggers. So we did that as well. Not here. Here we try to exploit the kind of the complex relationship, hopefully get those extremes with the 3D function that we got. But I agree with you that it might be interesting to focus on the very extremes, because biologically speaking, something different might happen. So there are studies that show that heat waves might add something to the continuous, non-linear exposure response function. There will be something with the heat waves which goes beyond the simple exposure response functions we are seeing here. Yeah, thanks. Yes.
It's a very great project. And my question is about the tensor smoother product. When you form the tensor product, for example, PM2.5 and a high temperature, have you ever adjusted for ozone and the PM10 in the tensor product?
So this is a good question. Definitely not for PM10 because usually when we investigate PM2.5, adjusting for PM10 is kind of counterintuitive. One is part of the other. So you would change the interpretation of the coefficient because usually since one is contained in the other, adjusting for one would mean kind of make your inference on the residual part, which is the coarse fraction. This was not something we really wanted to do here. So we didn't adjust for PM10 when we investigated PM2.5 or the other way around. For ozone, I think in some of the sensitivity analysis we did that, and it didn't change much. So we didn't change. It didn't change our relationships. Definitely, we did that in the next project that I will show. So there was not a lot of residual confounding from mutual co-pollutant exposures.
Is it reasonable for when adjusting PM2.5? The coarse particularly.
So what people do if they want to focus on the coarse fraction, the simplest and naive thing you can do is to subtract PM2.5 from PM10 ahead, so to get a sort of estimate of the coarse fraction. I say it's naive because to do that, you should have exactly the same monitors, make sure that they are monitoring exactly the same way at the same time. And then you get some kind of realistic estimates of the coarse fraction. But even so, you are mixing together measurements which are taken with some errors. So you are adding up errors in the PM2.5 estimates, errors in the PM10, and so that what usually happens is that the signal you see in the coarse fraction, the way you have defined it this way, is more noisy because of this exposure measurement error which comes from both fractions. But conceptually, investigating the coarse fraction is very interesting because coarse fraction has possibly by different sources of air pollution. And so it might be interesting. For example, natural sources in Southern Europe, we have a lot of intrusions of desert dust from the Sahara that impacts more the coarse fraction and less the fine fraction. So investigating different fractions might be interesting. Okay. So we move to the next. Okay, so the MCC Collaborative Network, for those of you who haven't heard about, is a collaborative network of investigators from all around the world. People preparing data on a voluntary basis, basically. It's anonymous data. It's aggregated data. It's daily counts of mortality, daily mean temperature, daily mean air pollution for all cities around the world. It is led by the London School of Hygiene and Tropical Medicine as an enterprise. It's a big effort, but the nice thing is that people can volunteer to run to conduct a study. So there is a protocol to fill, you send it to the steering committee. Usually they are okay, or maybe they can put you in touch with people doing something similar within the same network. You get the data, you run the analysis. So it's a good opportunity for all of you that might be interested in working on this time series data to know about the MCC Collaborative Network. Yes, this is summarized here. Of course, the representation is not perfect. There are areas like most of Africa, which is not represented, other areas in Asia, not represented, only a few locations from Australia, but that's one of the limitations of a voluntary-based, collaborations. Okay. So what we did here was to investigate whether the association between air temperature and mortality is modified by air pollution, exactly as before, but also the other way around. So to evaluate whether the association between air pollutants and mortality is modified by air temperature. And then we tried to see whether there was any, differences across different countries, across different continents, try to have a kind of a perception of the heterogeneity of the results. Very briefly, this is the distribution of the cities. This is temperature. This is PN10 average. So we use daily averages, but of course for the map we use the average across the entire 10 series. And this is PN, this is ozone and PN245. And we have an NO2 as well here, which is not in the map. Small, very big table with a lot of numbers. We will not go into that, just to give you a flavor of the variety of the countries which are involved. Does any one of you know about the MCC network? No? Okay. Introduction. So again, some similarities with the previous studies and some differences. Again, here we focus the attention on the warm period. One of the comments of the reviewers, why are you only doing warm, why not the cold period? Because it was too big, would be another paper, doing also the cold effects. It's very interesting, but it was matter for another. In this case, we couldn't just define based on calendar months, we had to adapt to each different country. And the best could think of was to consider a running average of the monthly means and to define as the warm period the 6 consecutive warmest months in each country, in each city, sorry. This is what we did. So we have a continuous time period because it's consecutive months. It might shift a little bit from one place to the other, but that was exactly the point. And in sensitivity analysis, we restrict the warmest months. Again, it's time series data by city. So in this case, we don't have a big area, small area. It's just the city, the country, and the continent. Yes. So we have a time series for each one of these 620 cities. And we analyze them with using, again, Poisson regression, followed by country-specific, and then some global meta-analysis. Again, both the exposure, in this case, we don't have just one exposure. All of them are exposures, all of them are effect modifiers. So, because we study both sides of that 3D relationship. And all of them were analyzed at the lag 0.1 for the same I mentioned before. In this case, we adopted a different approach. So we applied a product term between a cubic spline for temperature and a linear term for air pollution. And the reason for that is that one of the nice features of the MCC is that before going to external review, you go to internal review. And in this collaboration, there are a lot of big, epidemiologists giving you insights. Joel Schwartz, Michelle Bell, Ben Armstrong, all big names. And many of them were not convinced about using air pollution as nonlinear. Originally, I had used the tensor smoother exactly as showed before. But then they said, okay, it's difficult to explain. It's difficult because one thing is to report the effect of temperature by air pollution. But when you express the effect of air pollution, what does that mean going from the, from the 25th to the 75th percentile? It's totally different levels. So the adaptation thing, we can kind of easily understand it for temperature, that it is relative because of adaptation, and so you want to keep it relative to each location. But when it comes to air pollution, it's not that easy to understand that you should be relative. I mean, 20 micrograms is 20 micrograms. although there might be still some adaptation there as well. There are places where, on average, they have 50 or 60 microgram per cubic meter and they do not die every day, all of them. So there is some adaptation, but still it's not like Earth temperature. And also all of the literature uses, usually linear terms, 10 micrograms, etc. So because of all these comments, I switched to this approach, which is non-linear air temperature, linear air pollution, still exploiting the 3D relationship, but with some further constraint. And then we have usual confounders, which are long-term and seasonal time trends and day of the week. Okay? And it was not all-cause mortality here. We didn't have cause-specific mortality in this study, but we did cause-specific mortality in another study from the MCC. So here, the air pollutants are the relative risk of mortality are expressed per 10 microgram per cubic meter increment in air pollutant. Okay? And we express that overall to see what was the effect of air pollution per se. And then by changing temperature levels from the first to the 100th percentile. So we're kind of more continuous here. And the reason was that the internal reviewers told us, why are you just picking up a few percentiles? Why don't you explore the full range of the effect modifier? And the same we did for, we expressed the relative risk for increments of air temperature, from the 75th to the 99th percentile of city-specific distribution, but then we changed exposure levels from 10 to 150, but this is pollutant specific, and the range of the pollution was based on the common support of all the cities involved when temperature was between the 75th and 99th. So it's complicated, but the idea is that if we are expressing the effect of temperature by 75th to 99th, maybe in that range you never had air pollution below some values or above some values. You are restricting your effect modifier range. And so we tried to find ranges which accommodated most of the cities in the analysis. Is that clear, more or less? Okay, so these are the main effects. So before going into the effect modification, let's just see what kind of main effect we found. So this top part is temperature. So in the main model, we analyzed 620 cities. We found that when temperature increased from the 75th to the 99th percentile of city-specific distribution, on average, globally of the 620 cities, mortality increased by 8.8%. Which is quite a strong association, which is very similar to what is found in the literature, also from the MCC. And this is what happens when we start adjusting for air pollutants. So if we adjust for, and you see the number of cities changes because not all of them, not all the 620 cities had data on all pollutants. So in total, we had 620 cities, but the combinations were different depending on the availability of one or the other. But interestingly, despite the different mix of cities, the results were quite robust, I would say. Here we had to use like 0 for PM2.5 because PM2.5 was mostly contributed by the US. But unfortunately, the US doesn't provide, it provides data every third day for most of the years included in the data set. And so it was impossible to have 0-1 averages. I mean, we could have it, but at the cost of losing a lot of information. So we prefer to use like 0 for PM2.5 in order to preserve as much information as possible. But still, you see similar results. And then these are sensitivity analysis, different ways of, so season defined as the 3 warmest months, similar effect. Time trends analyzed with different degrees of freedom. I mean, these are details. You can see here that when you start expanding the lag, the effect drops, and this is expected. As I was saying before, it is most of the effect is concentrated in the very first days. If you dilute it using a more delayed time window, the effect will go down. And yeah, this is instead of using the 75th as reference, what if we use the 50th percentile? And the results is a little bit bigger because the 75th is already in the increasing part of the curve in most of the cases. And these are the effects of PM10, 10 microgram per cubic meter increments, PM 2.5, ozone, and NO2. The magnitude of the association is much smaller. Again, this is totally in line with the literature. But we found the results which are very much in line with what has been published by the MCC Collaborative Network in very important papers around. So 0.4, 0.6, 0.3. So small effects, but you can see very precise. So very narrow confidence intervals. Okay, so then this is a very simple example of what happens when we start investigating the effect of our temperature by levels of pollutants. And what we see here is that basically, apart some flattening here, but with very large confidence intervals, we see quite a clear increasing gradient of the effect. So the effect of temperature is more and more high, higher level of PM 2.5. For PM10, the flattening seems kind of more pronounced. So maybe there is really something going on. So at some point, you have some maximum effect in that. It's also to be said that at this point, the number of cities start to become very small. So the case mix of cities included in each value of different concentrations is different. So that is also why you see larger confidence intervals. Ozone and NO2. So pretty much the same picture. While when we see the other way around, so these are the effects of different air pollutants by levels of air temperature. We are still in the warm season, so even at the 0-10 percentile, it's not very cold. We are still in the 6 warmest months. But what we can see here is that apart some up and down, there is a sharp increase in the effect of air pollutants when temperature percentiles are the highest. So it's not an increasing gradient, it's kind of some up and down, or maybe some more or less stable effect, and then there is a sharp increase at the extremes. This is also the case for ozone, even more pronounced. While for NO2, it's not that clear actually. So it goes down, it goes up, but here it's pretty much similar to what we see here. So we don't see, so we see heterogeneous effects across levels, but we don't really see a trend that we can compute on. Okay, these are just a few figures of what happens in the different countries. We couldn't go much deeper into that because it's a huge study. I mean, it would be interesting to investigate why there are these differences, what kind of a country or city-specific characteristics are responsible for these different slopes. We didn't go into that level of details. But what we see here is that there are some places, Europe is kind of popping out always, very sharp increases in the effect of temperature by increasing level of air pollutants, so the red one. And Australia, it's only 3 cities. It's not really Australia. So one of the limitations of the study is that it's not representative of the whole count. It's representative of the cities contributing for that count. So, but we had to give some label here. So it's the 3 cities in Australia present these results, while in the US, for example, which is here, there is some increasing effect here, not much going on. So there are differences. And the same is true here for ozone and energy. So this is interesting to explore. While, yes, that's, yeah. So in conclusion, we did find adverse effects of high temperatures and air pollutants. So we confirmed what is known from the literature. We also saw stronger effects of high temperatures on days with high pollutant concentrations And that was kind of a sort of a smooth increasing gradient of effect for higher levels of ventilation. While we also found a stronger effect of air pollutants when temperature was highest, but with a totally different pattern. So the effect was totally concentrated in the very extreme days of temperature. And also some high levels of heterogeneity in the results across regions and across countries. Yeah, I think that's all.
Yeah, I think we have time for maybe 2 or 3 quick questions. I know you all submitted questions through Canvas, but now would be a good time to ask.
Was it clear? Or was some part that I totally lost? Yeah.
I guess one question I had for the both studies was in the sensitivity analysis, you considered the lag from 0 to 10 days as potentially more accurate in a sense because it's maybe considering for mortality displacement of the first couple of days, or if that was less relevant to the study because you were looking at the association between heat and air pollutants rather than like the effect.
So this is a good point. So mortality displacement, we haven't really analyzed that. If it was true that after a peak in the effect on the first days, there is a drop, even a protective, in the next days because of the depletion of this acceptable population, I could say that maybe a 0-10 is a more realistic, picture. But that is not certain. It can also happen that there is a very sharp increase at the beginning, and then the effect is not there anymore, it's flat. And having a 0-10 would dilute, you would not see what's happening when there are peaks in air temperature for a few days. So to me, it is more the second than the first. I would consider the 0-1 or 0-3 a more accurate picture of what's happening when it's hot because of what the literature tells us about, heat waves and how mortality increases exponentially immediately when you have such triggering, environmental trigger rather than going. But of course, it would be interesting to investigate the displacement, maybe even over a longer time period. In addition to that, yes, here the focus was on the interaction. And for air pollution, there is not much in the literature in terms of mortality displacement, while there is something for temperature. So I think that is, we had to keep it simple for the ease of interpretation.
Question?
Yes.
Thank you for your talk, very clear. And my question is, in the MCC project, did you ever try to analyze the relationship, the interactive effect in different climatic zones? Maybe in some very hot areas, hot rooms, they may have different, the interactive effect. The hot area compared to the cold area, maybe they have a different relationship.
As far as I know, in the MCC, the only project which dealt with the interaction between air temperature and air pollution is this one. Because if there was another one, the steering committee would have put us in action and we would have done that together. In this one, we didn't go into that level of detail, but that would be definitely an interesting development. So we see there is the heterogeneity. Why is that? We have 620 cities. So ideally, we might collect for each city some city-specific characteristics, for example, the climatic zone, or other characteristics that might explain that heterogeneity, and see, once you account for those, how much the heterogeneity reduces, or how they modify that. So that would be a good development.
Yeah, like building off of that, that was one observation I had, is that Europe is kind of a more homogeneous climate than Asia or North America or South America. Like you can even see just by latitude where the cities are. So I wonder if just sort of subgrouping within continents, you could get a stronger signal there.
Yeah. that is one of the reasons for the exhaustion. So we were in Europe, we had Norway and Greece, and we tried to do country-specific analysis, and we did see very large differences between Norway and Italy, for example. Here, we might do the same. One problem also is in the labels. When we say, Australia, 3 cities, even in Asia, it's mostly the Eastern Asia, so it's not very well represented. So that is one of the limitations, that we don't have a lot of representation of some areas to explore this kind of gradients. But yes, we could do that. Thank you.
Great, I think we're perfect on time. Thank you, Massimo. Online, and as a reminder, we have this holding of the seminar posted on the Yale Center on Climate and Health YouTube channel. So thank you everyone for joining. And the food is in the room 108.